everyone. Thanks very much for coming. Today we have the honor of having Arthur Van Kamp, who graduated from Ghent University this past January, and who is now a postdoc at Carnegie Mellon with Teddy Seinfeld. And Arthur today is going to talk about choice functions as a tool to model uncertainty. So please welcome Arthur.
Good afternoon. Thank you for the invitation as well. Thank you for the arrangements, Robin. I'm really glad to be here. Before I actually start, I want to shortly introduce myself. I defended my PhD and obtained my PhD in January of this year from Ghent University in Belgium. And my two promoters were Gert de Koopman and Enrique Miranda. Gert de Koopman is a professor in Ghent University, and Glenn will give a lecture there in 2 weeks with him. And Enrique Miranda is a professor from the University of Oviedo in Spain. And until the end of December this year, I am a visiting scholar at Carnegie Mellon University, and my host is Teddy Seinfeld. So now, what do I want to talk to you about today? I want to talk about choice functions, and an important special case of it, sets of desirable gambles. And I want to argue that choice functions and sets of desirable gambles are very elegant, intuitive, and simple models to describe your uncertainty. So they are very easy to work with. And now, in order to put this a bit in perspective with the other theories of imprecise probabilities, I used the picture of Robin Gung's presentation last month with her permission. And this was in her introduction. What you see is basically you see subsets of theories, and the most common theory is the classical theory of probabilities, and then every superset of it is like a generalization. So you have an increasingly more general theories, and in particular convex and closed sets of probabilities and arbitrary sets of probabilities I want to link with it today. So I want to talk about choice functions, and in particular special case sets of desirable gambles. Sets of desirable gambles, sorry. Yeah. And I think it will add to this picture in another way, because every model here is either a probability model itself or something like a partial order that can be represented uniquely by a probability or by a set of probabilities. And therefore this model is what we call Archimedean, and this means that it has a suitable continuity property in order that this continuity property guarantees that it is equivalent to a probability. Now what I will talk today is about a non-Archimedean theory. So it will not be equivalent to probabilities. It replaces probabilities in a sense. And therefore I would like to add to this picture in this way. Sets of desirable gambles. You can think of it as a non-Archimedean or the not necessarily Archimedean counterpart of convex and closed sets of probabilities. In the sense that every set of desirable gambles, it has a corresponding convex and closed set of probabilities. But this is a many-to-one relation. You may have two different or many different sets of desirable gambles that have the same corresponding convex and closed set of probabilities. And the same way for choice functions. A choice function every choice function has a corresponding arbitrary set of probabilities, but it's again a many-to-one relation. And therefore, a set of desirable gambles you can think of it as a generalization of a convex and closed set of probabilities, and a choice function as a generalization of an arbitrary set. But also I want to mention that here, with closed and convex sets of probabilities, the generalization sort of branches out. A set of desirable gambles is still convex, while an arbitrary set is not. So it's neither one of those two is more general than the other. This is not convex. This is still a convex theory, but this is not non-Archimedean, and this is Archimedean. And both theories are kind of unified by choice functions. Okay, so in order to start off, I will start with something that I think everybody will agree on. It's in the field of imprecise probabilities. And imprecise probabilities is an attempt to generalize classical probability theory in order to take indecision and imprecision seriously. I think everybody can agree on this. Yes?
So I've been wondering about this exactly statement. So I've been thinking that the imprecision sometimes we have in mind is more fuzzy than imprecise probabilities, where you have, say, a set of probability functions, but they have still sharp boundaries. What is included and what is not included. So you can assign integral value probabilities, but it's still sharp boundaries. So it's not quite imprecise in the sense that when we say, fuzzy or vague.
I agree with you, but I would say that it depends on the interpretation that you attach to it. And I would argue that, for instance, if you work with a set of probabilities, it's non-exhaustive, this interpretation. In the sense that if I have a set of probabilities, my actual belief may be contained in the set. But I will not say it. I will only say this is my set of probabilities, but I will not say whether it's exhaustive or not. It may be not exhaustive. I may not tell you everything I want, and therefore therefore you can circumvent the sharp boundary by just telling something more general. I will work in a personalist view. So the probabilities is a reflection of your beliefs, of a person's beliefs.
I didn't quite follow the part about non-exhaustive. So what about non-exhaustive that you can say is fuzzy?
Well, it's not fuzzy theory. It's something else than fuzziness. But
so what about sharp boundaries?
Yeah.
I can say, well, here's my set of probability functions.
It all depends on the interpretation that you attach to it. And I will add an operational interpretation to a set of probabilities later on in the talk. But I can mention that it's a non-exhaustive interpretation. If I have a set of probabilities, for instance, the interval point or 1/4, 3/4, if this is my belief model that I give to you, it may be non-exhaustive. It may be that I believe it's 1/2 or whatever in between, but I will not tell it to you. So in this way, it's not necessarily a sharp boundary. I just gave an outer approximation of it.
There is a way to do this by taking a set of probabilities.
Sorry?
If I give you a set of probability functions, then that's kind of non-exhaustive in some sense.
A set of probability functions.
But still that is sharp because there are sharp boundaries of what is included and what is not.
I am not giving you a set of probability functions. I only give you an outer bound. And it may be sharp, it may be not sharp. In this specific interpretation that I will attach to it later in my presentation.
Right. So there's just something that we're trying to get at, but we just cannot get at with set theoretic constructions. But calling it imprecision might be a bit misleading here, right?
I'm not. Well, it depends on what you mean. What we mean by imprecision, right? I think later on I think it will be clear. But please interrupt me if it's not clear later on. But I will attach an operational interpretation to it. So in terms of betting behavior of people. So that's the next thing that I want to say. I want to warn you. It's a personalist view. It's like in the vein of the Finetti. It has to do with an expert or an agent or a subject, his beliefs about something, and we want to model this. And what is common, or what is the most basic reflection of a belief? Well, that's the decisions or the choices that a person makes when faced with uncertainty. So that's the basic idea. We will look at a subject, his choices. And so the first thing we need to know is, what do we choose between? Well, what do we choose between? We choose between gambles. How does it work? Well, consider an uncertain quantity, x, capital X. It's a random variable. It's something whose value is not known to you, or not precisely known, or not well known. But it assumes a value in a possibility space, curly X. I will assume for the sake of argument that the set is finite, but that's not necessarily most of the concepts I will explain. So, but let's assume that this is a finite set. Then a gamble is just a real valued function on this possibility space. So gamble is a vector with real components and as many components as there are elements in X. So we can depict a gamble graphically.
Maybe you can turn off one of the lights.
It's either or.
It's on and off. There's no dimmer.
Oh, so there wasn't a halfway.
No.
It's not a half.
So that's R plus, is that what we're saying there? Or to the X?
This is R to the X.
R to the X.
I'm fine with turning off. I don't know about you. For me, this is fine as well.
Oh, but what is it? X? What's the X? Oh, that X is an X. It's not an X. It doesn't have any others.
It's the curly X is a possibility space, the sample space.
Up there on the X. Okay. Okay. Gotcha.
Okay. So any gamble, for instance, consider a coin toss, and the outcome of the next toss is unknown. This is a two-dimensional experiment, so I can work in a 2D plane, and any point in this plane is a gamble. For instance, this one. How do you read it? Well, this gamble f is determined by its first component, which is its value in heads, and its second component, which is its value in tails. So any point in this plane is a gamble, and this specific gamble, it has a value 1 in heads and -1/2 in tails. And what is now the interpretation that we attach to a gamble? Well, a gamble is an uncertain reward. So what does it mean to have a gamble? For instance, this gamble, what does it mean? If the next toss turns out to be heads, then my capital is changed by 1 unit of utility in a predetermined linear utility scale. And if it's tails, then I will lose half of a unit of utility. So a gamble is a bet. And any function, any vector is a gamble. So now that we know what I will choose between, we need to know how to choose between, of course. And the first, or the easiest way to choose between gambles is just pairwise comparison. I take any two gambles and I compare them. And what we have then is a preference relation on the set of all gambles. And this preference relation is a strict partial order, and actually it's a vector ordering. So in vector ordering, it means that we can add a common gamble to both sides, or we can multiply both sides with a positive real number, with a common positive real number. So but this thing is actually a subset of the Cartesian product of L with itself, of the set of all gambles with itself. So that's quite, mathematically it's quite difficult to work with, but there's a very easy equivalent representation by it. And that's a set of desirable gambles. What is a set of desirable gambles? Well, a set of desirable gambles are the gambles that you prefer to 0. Now what is 0? 0 is a special gamble, it's a gamble. It's a constant gamble, it's the gamble whose payoff is 0 everywhere. It's a 0 vector if you want. And it's the gamble that leaves your capital unchanged whatever happens. So whatever the outcome is, you will not lose nor gain anything. And I will compare every gamble with 0. If a gamble is strictly better than 0, if I strictly prefer a gamble to 0, then I want this gamble. So a set of desirable gambles, my set of desirable gambles are the gambles that I want. And how does it work mathematically? Well, suppose that f is preferred to g. Then, since it's a vector ordering, f minus g is preferred to 0, and f minus g, hence this new gamble, is in my set of desirable gambles. So to summarize, my set of desirable gambles is a set of gambles that are strictly preferred to 0. So if I have a preference relation, I can find D, my set of desirable gambles, and vice versa. If I have a set of desirable gambles D, then I can go back to the preference relation. It's the same thing. But a set of desirable gambles is way easier to work with. A set of desirable gambles is just a subset of the gambles. It is very elegant to work with. Actually, it gives a geometrical flavor to probabilistic inference. it is of crucial importance in a number or a variety of theoretical works, for instance in predictive inference, in creedal networks, which are imprecise Bayesian networks, and so on. It's really very important, and also it's very general. They include convex and closed set of probabilities as a special case, and therefore all its special cases. And also it generalizes conservative logical inference via its device called natural extension. So it's really a very popular model. But is every subset of gambles a good one? No. Only the coherent ones, the so-called coherent ones. You can think of this in very much the same vein as a coherent prevision for the Finetti. Here it's a coherent set of desirable gambles. It needs to satisfy 4 rationality requirements. The first one, D1, if a gamble is negative, then it is not desirable. Now what does it mean? F is non-positive. It means pointwise. It means for every outcome or every component of f, of the vector of f, is 0 or less. Well, if that is the case, then in the best case, I do not lose anything, but there are cases in which I might lose anything, I might lose something, so this is for sure not strictly preferred to 0. This is actually the counterpart of the avoiding sure loss criteria of the Finetti. Then the second one, it says if a gamble is positive, then it is desirable. And what does this mean? A gamble to be positive, it means pointwise at least 0 and as a gamble not equal to 0. Or in other words, it means every component is at least 0 and there is one component or more components that are strictly bigger than 0. Well, if that is the case, in the worst case I do not win anything, but there's always an opportunity to win. There's always at least one outcome that let me win something. If that is the case, then it should be desirable, it should be better than 0. The third and the fourth axioms are actually just reflections that the utility scale is linear. The third one says that whether my gamble is paid off in euro or US dollar doesn't change its desirability. And the fourth one, it says that if I have 2 desirable gambles, then its sum is again desirable.
So to clarify, the second requirement, you said that the greater sign means that f is, you can be everywhere except for one place that is positive.
Yes, it can be 0 everywhere, but at least somewhere it needs to be strictly positive.
That you would call that to be strictly positive as a vector?
So it's not pointwise. This is not pointwise, this relation. It means pointwise bigger or equal than, and as a gamble not equal.
And then for the coherent sets of desirable gambles, so I should understand desirable as in relation to my own beliefs.
Yeah, this is your...
Coherent is like an external criteria to say that, because I...
Can you come again?
Because coherence and desirable seems to be similar, I'm just trying to, I guess, clarify on the terminology. So desirable is, this is in respect to the preference relationship, which is a personalist belief.
Yeah.
But coherence is an external requirement for me to be a rational agent. Exactly.
So I guess this is really, I mean, you didn't invent this terminology.
No. It's
so it's not fair to criticize you for it. But if we could criticize the person who did invent it, we might ask, why didn't he say desired gambles instead of desirable?
That's actually a good question, and I don't know the answer to it. If you want, I can say in the following desired gambles.
Well, I have more radical comments, but that was
okay.
Yes. Desirable sounds like something not personalist. It sounds like something objective.
Yeah, no, it's meant in a personal way.
What he said is the desirables I consider. It's the gambles I consider desirable. But he shouldn't have called it desirable then. He should have called it desired.
Yeah.
That's a ridiculous.
Was it translated from anywhere?
No, it was in English. He wrote it in English. Wally.
Peter Wally invented the term.
Yeah. Peter Wally, do you know anything about his existence? I forgot to ask you that. He seems to have reappeared, or he published.
I heard he published a new book.
So
Yeah.
has Gert heard from him? Does he know anything
No.
about it?
No, Gert didn't hear from him. But I know, that, for instance, that Enrique Miranda bought the book.
Who did?
I bought the
Oh,
Have you got it already?
Yeah, it's my office. It was $4
Oh,
on
sure.
Amazon.
Yeah.
It really was. Yeah.
How many dollars?
4.
4.
4.
what?
Yeah.
What?
I think I ordered it too, but I haven't gotten it. I thought it was more than that. It's bizarre.
You can only copy with $4.
Yeah.
I think that Harry had a question as
I
well.
ordered-
It's not disappeared, and now all of a sudden.
Yeah, Bert, from last time.
I ordered this coffee for $4. I wanted to order another one for Charlie. It doesn't let me. I'm a little sad. You can only buy one coffee at this price. The price is 66. And it decreased over the next month, all the way down to 4. I'm serious about that.
What's the name of the book?
BI inference, BI statistics, sorry.
Bounded
BI,
inference.
bounded inference.
Yeah, BI statistics. Okay, I'm sorry. to interrupt.
So,
I got a deal.
when you define D,
Yes.
I thought it was designed, it was defined, okay, I see what you're saying. So it was defined as all of the things that you would prefer to 0.
Yeah.
And now, okay, so what is this greater than, less than? Oh, I'm sorry.
Maybe it will help if I write it down on the blackboard, on the whiteboard. Can I do that?
Yeah.
It might be marked here.
Oh, is this just to say that if f is less than 0, that means every component is
Yes.
less than
This means that every component is 0 or less. This means that every component is 0 or more, and there's at least one component which is strictly
Okay, that's fine.
greater than 0. Yeah. Yeah. So a set of reliable gambles, I will consider only the coherent ones. What does it mean for a set of reliable gambles to be coherent? Well, these 4 things, but what does it mean graphically? Well, the first axiom says that this plane, this orthant, the negative orthant, is bad. The red thing is bad, can never be desirable. And it includes the borders, and it includes 0. The second axiom means that the positive orthant is good, is always desirable. It includes the borders, but not 0. And then the third and the fourth axiom, it just means that it's a convex cone. So any convex cone that includes the positive orthant and has nothing in common with the negative orthant is a coherent set of reliable gambles. For instance, this one. This is a cone, a coherent set of reliable gambles. Let's go on. This one as well. I added some gambles here. Can I keep on adding? I can keep on adding. I can add for a bit, but I cannot keep on adding. I can keep on adding until I have a half space. In this case, a half plane. Because what would happen if I have a gamble here and here that are desirable? Well, I would add them, and the result would be something here. Hence, by D4, this should be desirable, but by D1, this can never be desirable. So, the maximal ones, in a sense, or roughly speaking, the maximal ones are the half spaces, the half planes in 2D. Why do I say roughly speaking? Well, because I haven't said anything about the border. It might be that one border is included, another one not, but I will not go into this in this presentation. So this is a maximal set of reliable gambles, and actually it corresponds, or such sets of reliable gambles, they correspond to a precise probability model, as we will see later on. For instance, this one is another one, and this is a very interesting one. What does it mean? What is this line? This line is the second diagonal, if you want. So it's a line of gambles whose value in heads plus value in tails is equal to 0. So every desirable gamble in this model is a gamble desirable if its value in heads plus its value in tails is bigger than 0. Or in other words, if its uniform expectation is bigger than 0. So this is a set of desirable gambles that corresponds to a uniform belief between heads and tails. So probability 1/2, 1/2 if you want. But I want to stress that I do not work with probabilities. This is my primitive model. Not a probability model, but such things are my primitive models. And this would correspond to a uniform probability model. But not every set of reliable gambles is a single probability or is uniquely determined by a set of probabilities. So there are multiple maximal set of probabilities. Are there also minimal ones? Yes, there's one minimal coherent set of desirable gambles. It's just a positive orthant. Why is it? Well, the positive orthant is a convex cone that that includes a positive orthant and has nothing in common with the negative orthant. So it's a coherent set of desirable gambles and it's the smallest one. We therefore call it the vacuous model, and it corresponds to the set of all mass functions. It's a model if you don't know anything. Okay, so let us now make the connection with sets of probabilities. And I guess at this point, I should clarify to your question that this is not exhaustive. This is just, in this picture, I have said to you what gambles I find desirable, are desired for me. I haven't said that those gambles are not desirable for me. I haven't said that. It can be that they are desirable, but it's just I don't want to say it to you because I want to be held responsible for things that I'm uncertain of. It's the minimal thing that I want to say. It could be that I believe more, but I just don't want to say it to you. So that's the interpretation I attach to it.
You gave earlier. You promised an operational interpretation.
Yes.
Is that still to come?
I think it's here.
So I want to object then that I do not think this set of desirable gambles concept is operational.
Because you need a rejection for it, or?
Well, because go back to that set of desirable gambles slide.
Yes.
If you would. So, where's the operational content? If someone you're just saying these gambles are desirable.
Yeah, and it's.
But if I offered you one of them,
I would be obliged to take this bet.
You would say, wait a minute. What does he know that I don't know? Right? If I offered you one of those gambles, you would think again. Wouldn't you?
You mean if there's time involved, or?
You're going to put these gambles out for anybody to, these gambles, if they represent what you think and your information.
Yes.
They don't necessarily represent what I know.
No.
Maybe I know the answer. So are you going to gamble with me if I
no.
give you one of these
yeah.
gambles?
I see. No. Okay.
I see no operational content whatsoever here. I see no way.
Because I would bet against another people then. I would bet against another person in this case.
Well, how else is it going to be operational? And that's my...
No, I agree with that, but...
Are you suggesting that all personalist beliefs are not operational? Because I could only act upon what I know of what's out there. And if I know for certain that I don't have all the information in the world.
I think this was based on Di Finetti, and I would make the same objection to Di Finetti, and Di Finetti accepted that objection and decided he wanted to use proper scoring rules instead.
Yeah, I'm aware of that. Yeah.
So I think the argument applies here. That's my comment.
No. Okay, in this sense, I would agree with you.
That's my objection to the claim that this is operational.
So,
Go ahead. Okay,
I don't want to.
I know there's a paper about from Ghent and Eric Quagebeer and Philip Hermans that at least they claim to make it operational in the sense that they work with rejects, and they say, I reject the gamble, this is operational. And they can retrieve the full picture of this positive thing, this positive assessments by the rejects. But yeah, I have to think a bit about it.
Or that you would, so if you think something is, I mean, that's a possibility. If you don't, I suppose if you think nobody knows, so that's a possibility. You'd be making gambles you would make against anybody. But that almost has some almost objective concept to it. There's some objective probability, some residue that nobody could know. So I'm willing to make at least those gambles I will take because they're kind of a residue where nobody knows. But that kind of doesn't sound very personalist to me anymore. It sounds much more objectivist.
Because you don't bet against a person, but still it's it's...
Oh, you don't bet against a person?
Or
I don't understand. I should look at their paper. I guess I didn't understand what you're telling me.
I bet that I don't understand fully. But
Okay.
can I go on for the time being, or?
I'm sorry. Yes, I stopped.
Okay. No.
Well, I was
Yes?
wondering what, what's the objection to operation? So if I say, if I have a set of things and I say to myself, I mean, I don't have to advertise them ahead of time, do I? I mean, if I have a set of things and I know that if I'm offered this bet, you know, for example, I know that if somebody walks in the room right now and says, "I'll give you 2 to 1 on heads," and they're going to toss a coin, I'm going to take that bet.
But
Isn't that operation?
If you want to express your probabilities about rain, whether it's raining right now, you might have some opinions, but if somebody walks in the door who knows because they were just outside, you're not going to...
Well, then I should update my opinion.
You should update on the basis of what they say, whether or not they will accept your gamble. If you have on the table, these are my desirable gambles, I will take any of these gambles, and somebody walks in the room and offers to make one of them with you, then you're going to say, no, wait a minute. That's new information that you're willing to do it. Because they know more than you do. Yeah. So is this something, so what is operational about it? It's not like you put it on the table and said, I'll prove that I'll take these gambles. That's my objection.
So there seem to be contexts in which you can operate and contexts in which you wouldn't, right? And so it's not an absolute thing as maybe is being suggested.
So the context, and I'm asserting the context in which you would take all comers is not just, if you take that to be the context, where I'm saying here's these gambles and I will take all comers, you must have some objectivist concept of those probabilities. They aren't just your beliefs about what is true. That's my objection and claim, and which I insert, and I apologize if I'm slowing you down too much.
No, not at all.
Yeah, so I'm not sure how this addresses my earlier concern about precision and sharp boundaries. So I mean, suppose, let's go to the next slide. We have, I think the definition of PPOP.
Yes,
right.
but I will explain it. But
Okay.
yes.
Yeah. So suppose, I'm considering gambles about rain and non-rain states, probably attached to rain and non-rain states, and rewards and punishments, right? And suppose there's a series of gambles I am willing to accept. And there is...
And the series of gambles you would not accept? Or?
I will.
You will accept?
I think they are desirable.
Yes.
Right. And they will correspond to the set of my desirable gambles, right?
Yeah,
And that will be a set with precise membership relation, which
of course,
gamble belongs to that, and which one doesn't belong.
Yeah, it's not a fuzzy set. It has a precise membership relation, but there's a bit discussion about whether it's really operational. But the operational meaning is that it's not exhaustive, or the idea behind it.
I'm not sure how the notions of operational or being non-exhaustive help here.
Well, and it could be that my belief is stronger than this. That I actually believe that these gambles are also desirable, but I just don't want to say.
There's a true fact about what you believe.
Sorry, can you come again?
So are you saying that there could be a true fact of what you believe? It's not represented by this picture. Like there's a precise probability.
This is what I want to. This is what I want my. Sorry, this is what I want to commit myself to, in a sense.
But this minimum commitment set has a precise boundary. Yes.
Yes, yeah. I agree with that. Yeah.
But then how does fuzziness come out?
Fuzziness will not come. It's not fuzzy. It's imprecise.
I mean, so my paradigm of imprecision is that not only there's interval value probabilities, but also there's imprecision on the boundaries. There's no sharp boundary say 0.2 is the lower and 0.5 is higher.
Okay, but then I have another idea of imprecision.
Sorry.
the word.
It's one part of the word imprecise probabilities. The other part is just we're trying to get to this notion of imprecise probabilities, right? This notion that we have in mind that, you know, 0.1 is too precise because then you make a mistake. And, you know, even 0.1 to 0.2 is too imprecise too. It's too precise too.
Okay, can I ask you a question?
Yeah.
Is this too precise yet, still?
What is this?
This is the set of desirable gambles, the vacuous one it's called, and it's my only desirable gambles are the positive orthants. So the only gamble I find desirables, the only gambles I find desirable are the ones that I will gain something, and nothing else. So that's the least committal set of desirable gambles. Yet it has a precise membership function. So in the interpretation that I attach to it, this means to not believing anything at all about the problem, not knowing, not having any information about it. And still it's a set with a precise membership relation or function. Is this imprecise for you or not?
I mean, it is imprecise to some extent, but it's not imprecise enough. I think there's improvement from, say, giving a precise probability function. Definitely it's improvement, giving you more choices in between. But it is still not enough in precision.
Okay, okay then.
And I mean, it's somehow, I mean, there is the paradoxical element here too, in the sense that since we cannot get away from precision, maybe there's no way to use a set probability anyways. If you think that, well, the reason we go from 0.1 to 0 to 0.2 is because 0.1 is too precise. But if 0 to 0.2 is still too precise, then
it's not necessarily too. The precision that okay, but I think it's a play of a game of words. But the imprecision that I want to address is not that a number is too precise. No, it's well, the number on itself. It's not a problem. The problem is that it's too committal for me. I want to be held responsible only for this in this case, only for those gambles. But I guess it's merely a game of words, and it's not a fuzzy theory. It's what is commonly used or referred to as imprecise probabilities, and so it's no fuzziness involved in it.
Do you know any models with more fuzziness in the theory?
I know about a guy. I forgot his family name, but his given name is David. In Spain, I think he worked with fuzziness and imprecise probabilities.
There's a vast literature combining these ideas.
Oh.
Zade is fuzzy.
Yeah.
Wrong?
No, yeah, but
there are many people who have written papers combining fuzzy with whatever, including this.
Yeah. But one of the problems I would argue with this fuzziness is that it has no clear interpretation, I guess.
No what?
It has no clear interpretation.
Yeah.
What does it mean for an element to be half a member of a set?
But
and half not?
The fuzzy set relation, I think, is too precise because there's a precise.
You're a hardcore.
Fuzziness level equals to 1. Then there's going to be completely non-fuzzy membership even then. So I just feel like it's unavoidable, the precision in the model.
But then at least we need a sound interpretation for it, I think.
Well, so the way that I think of it, you should correct me if I'm wrong.
Sure.
If you compare, so you had this motion picture of, you had the vacuous model and then the half space being the most precise model, right? So essentially what happens in these two triangles, in this and this area would be that if suppose that this is the truth, and whereas you claim that the vacuous model is what you endorse, then if any gamble that falls into those triangles in the second and the fourth quadrants, you would say that I would not make a decision, right? I would not take up that gamble, but at the same time, it's not to say that I think it's not desirable. It's not something I claim to be desirable.
Yeah.
So that's kind of a stepping back from taking an action or committing yourself to anything. So, and maybe that is the kind of imprecision that comes out of this.
Yeah, but I agree that
there are situations that I will claim that I know nothing of, or I would not do. Whereas if you have a probability model like this, there is no space for you to say that I do not take. It's either that I decline or I accept.
Right. I mean, there's definitely more imprecision in the model. Yeah,
Yeah.
I agree.
Yeah. I think, I know about your problem. I think, because we've talked about it in your
Yeah.
presentation too. I don't know of any constructs even that's mathematically expressible that could get it.
Yeah, it's very frustrating, I think, because there are certain phenomena that cause for this kind of fuzzy representation, but there's no mathematical model.
Okay, shall I go on? Yes. So we have a set of reliable gambles. I want to stress that this is my primitive model. So I don't start with a set of probabilities or what else. I start with this, and this is my beliefs. Now I want to make the connection, of course, with a set of reliable gambles, or at least given this, I want to define a convex and closed set of reliable gambles. And how does it work? Well, I will do it through a coherent lower prevision. What is it, a lower prevision? Well, a lower prevision is a functional on the set of gambles. So it takes as an input a gamble, and an output is a real number, just as an expectation operator. The lower prevision of a gamble is the supremum of all real alphas for which f minus alpha is desirable. Now, what is f minus alpha? F minus alpha is I receive f and I give away alpha. So I buy f for the price alpha. And if f minus alpha is desirable, well, then this transaction of receiving f and paying alpha is desirable to me. So the lower prevision of f is the supremum desirable buying price to me. And how does it work graphically? Well, graphically it's quite easy. I have a gamble, for instance this one. I subtract alpha. What is alpha? Alpha is a number, so it's a constant function, a constant gamble. So it lives on the first diagonal. And if I subtract positive alpha, then I go along this line. So I start with f, I subtract alpha, increasingly bigger alphas, until I reach a border. And at the border, that's the horizontal distance between my gamble and the border, that's its lower prevision. And that's the same thing as the vertical distance. So that's the lower prevision of my gamble f. This already tells you why sets of desirable gambles are more informative than lower previsions, and because lower previsions are equivalent to convex and closed set of probability models, also than that. Because it doesn't matter whether this ray is included or not. I take the supremum, so if this ray is excluded or included, this value will be the same. And that's exactly the non-Archimedeanity that does the trick for desirability. And actually that simplifies things, as I will show later on, such as conditioning. Next to a lower prevision, we also have an upper prevision. It's the infimum of all real betas, for which beta minus f is desirable. Now what is beta minus f? Beta is receiving beta for giving away f. So it's a selling price for f. If I have a gamble f, how much do I want it? How much utility do I want it in exchange for it? And it's an infimum of all such desirable transactions. So it's infimum desirable selling price. What is it graphically? Well, just very much the same thing, but instead of f, I work with minus f here, and then I add betas until I reach the border, and then the distance between it is the lower prevision. Now, one thing that's clear from this picture, and it is easy to prove, is that the upper prevision is always bigger than the lower prevision, or at least as big as the lower prevision. And that's because this is a convex cone. Now, what would happen if I actually have a half space? If I have something like this, well, then this picture is point symmetric around 0, and both are the same. They are equal. And this is for any gamble. So as soon as I have a half space, then for any gamble, its lower and its upper prevision are equal. It's because it's a point symmetric picture. So I have two functionals. Do I need both of them? No, actually I only need one of them. I can choose which one, for instance, the lower prevision. Because if I have the upper prevision, I can replace beta by minus alpha, and then I can bring a minus sign out of the infimum. It becomes a supremum. So I have that the upper provision of a gamble, f, is minus the lower provision of minus f. So if I have a lower provision for any gamble, I immediately have the upper provision for any gamble. So I'll focus on lower provisions. Now actually, there's done much work about lower provisions on its own, without having them derived from a set of desirable gambles. So, and its interpretation, or its idea then, is that it's a lower bound on an expectation operator. But in order for it to be coherent, it needs to be bounded, positive, homogeneous, super additive, functional. So what does it mean?
Can I ask a question?
Of course.
Yeah, the next.
This?
So if I look at the lower provision is the price I'd be willing to buy.
Yeah.
Provision is the price I'm willing to sell. Right?
Yes.
Actually, let me think about this and I'll come back. If I still have a question, I'll ask it.
Okay, sure. Okay, so lower provision, it's if you want, it's a boundary on the expectation operator, if you want, and it satisfies three things. It's bounded, so it's always bigger than the minimum. Graphically, it's very easy to see. If you have a gamble, well, what is its minimum? It's its minimum coordinate. In this case, it's tails. And this is always smaller or equal than the lower provision. Now, when is it equal? That's very easy. Well, it's equal if this ray is actually here. So if my set of desirable gambles is a positive ordinate, then here I have an equality for every gamble. And that's actually quite intuitive. If I don't know anything, then the supreme desirable buying price is just the minimum that I can win by this gamble. I will not, I won't buy anything, I won't buy it for anything more than that. The second thing, the second requirement is that it's positive homogeneous, so I can take out any positive lambda, and that just follows from this picture. Nowhere in this picture it matters, it doesn't matter where I put the unit. Everything scales. And then the third one, it's super additive, so the lower provision of a sum of two gambles dominates the sum of the lower provisions. You can see it in this picture quickly. These are two gambles, and the lower provision of the sum is bigger. Yes?
So f could sometimes be negative, right? One of its...
Yes, f can be everywhere.
So can the lower provision be negative?
Yeah, sure, yeah, of course. The lower provision, for instance, of -1 will be exactly -1, whatever your model is. The lower provision of a constant actually is equal to a constant.
This P should be, it would be easier to, if it were an E, it would be easier.
Yeah.
Yeah.
I keep thinking about probabilities.
I agree with you, yeah. Yes, it's an expectation operator. I should have replaced it with E instead of P. But mostly it's just P in the literature. But okay, so as soon as any functional on the gamble satisfies those three things, it is derived from a set of desirable gambles. What are the actions for upper provisions? It's also bounded, it's positive homogeneous, and it's subadditive. So now we have an interesting thing. If I have a half space, such a thing, then I already know from the previous slides that its lower provision equals its upper provision. So the lower provision is something that is both super additive and subadditive. In other words, it's additive. And also, if it's additive, then this works for any lambda, also negative lambdas. So it's actually, if I have a half space, then it's actually a linear operator. So therefore, it's a expectation operator. If I have half space, then this is a graphical proof that it's an expectation operator. So let us now go to expectation operators. Well, with any probability mass function, there corresponds an expectation operator in this fashion, and I collect all of them in this set. Now, given a lower prevision, I look at this curly M, the set of its dominating precise previsions or linear previsions, or previsions if you want. And what is it? Well, it's all the previsions that for any gamble dominate the lower prevision. And actually, this is a closed and convex set of previsions. And then there's a theorem by Wally. It says that the functional on the gambles is a coherent lower prevision if and only if this function is the lower envelope of its dominating linear previsions. And what is the lower envelope? Well, you take any gamble, it's the minimum of all the precise previsions and you let this minimum run over M. And this theorem actually, it shows that a lower or a coherent low prevision is equivalent to a convex and closed set of probabilities. So in this way, I have connected set of variable gambles with convex and closed set of probabilities.
And in this case, this would always be positive or 0. It will not be negative, right?
No, it's a prevision. P's are previsions, are expectations. Sorry for the notation. So the expectation of the function -1 is, of course, -1.
Can you say what is M again? This curly M, what is that?
The curly M is the set of dominating expectation operators. So this is a set of all expectation operators. If I have a lower prevision, then
On the top line, you wrote E sub P.
Yeah, I should have done it everywhere. I should have replaced every lower prevision and upper prevision by E instead of P.
But also your probabilities, you're writing P instead of...
Yeah, that's a small letter and that's a capital letter. But
So capital P means the same thing as capital E sub P.
Exactly. Sorry for the notation. Now I agree that I should have done it otherwise. Yeah, capital P's are previsions or expectation operators. So this says I have a coherent lower prevision, so a lower bound for my expectation operators. I take this set M of all its dominating linear previsions. That's actually a closed and convex set. And this characterizes completely my original lower prevision, just by taking the lower envelopes. That's the theorem of Wally, and it connects the language of closed and convex sets of probabilities with coherent lower previsions, and therefore also with sets of desirable gambles, which we have seen is more general than a lower prevision. Is that clear for everybody?
So the lower prevision itself is already the supremum over the set of prices that you were willing to.
Yeah. This is
And this is saying that the lower provision is coherent if it's the minimum of the set of lower provisions, such that they are dominating that.
Well, of course, if my lower prevision is a supremum of desirable prices, then it's coherent because my set of desirable gambles is coherent. I'm saying take any functional on the gambles. This functional is actually coherent low prevision if and only if this holds.
I guess I'm confused because the definition of the curly M involves P lower F.
Yes.
And this P lower, but that P lower F is not the same as...
It's the same thing, yeah. Actually, I didn't want to overload the notation. I should have, like in the index, I should have wrote P lower in the index of M.
But this is the P lower F that's defined as...
It's this one. So if we start with any functional.
Oh, you're just saying that if I were to derive the set of dominating linear provisions from this lower provision, and that this lower provision happens to also be the minimum of all of that,
then it's coherent. Yes. Exactly. Okay, so this was almost the end of the first part, the part about sets of variable gambles. This is a picture of Robin again. now I want to give you two reasons why this is actually very simple and elegant to work with. And the first reason is it's conditioning. Conditioning is very easy and always defined. If I start with a set of desirable gambles D and have a conditioning event E, what is then the conditional set of desirable gambles? It's D conditioned on E. Well, that's this set, the set of all gambles on E, for which the indicator times this gamble is desirable. Now, what is the indicator of E? That's just a special gamble. That's a gamble that gives 1 on E and 0 outside of E. And what is the indicator of E times F? Well, actually, that's a called-off gamble. That's the gamble that only goes true if E occurs. It gives you 0 otherwise, and if E occurs, then the gamble goes through. Otherwise, the bet is called off. Otherwise, if E doesn't occur, the bet stops. And I just look at which of those called-off gambles are desirable in my original model, and those called-off gambles, they define my conditional set of desirable gambles. So I think that's a very elegant definition. It implies Bayes' rule, it implies all the existing, or all the most informative existing rules. Yes?
So F, a gamble is a function.
Yes.
From X.
Well, this gamble is a function on E only. It's on the conditioning event, on the subset of X.
F is a gamble on E?
Yes. F is a gamble on E, and I multiply it with a gamble on X. Okay, this is actually not well defined everywhere.
But,
I define it like.
Okay, never mind. Okay, never mind.
Yeah, I take this to mean that this result of this multiplication is a gamble on X, on the whole space. And what gamble is it? It is a gamble that attaches 0 outside E and F on E. So it is actually a called-off gamble. So this is my conditional set of desirable gambles. Let's interpret it graphically. Now I need a 3D space, so it's a kind of more difficult picture. And my set of desirable gambles that I will be working with is the smallest cone that contains those 4 gambles. So you can think of it as the intersection of all the cones that contains it, all the convex cone that contains it, and it's also actually equal to the set of positive combinations of those 4 points. So take any of those 4 points, multiply it by a positive number, and add them together. It's this set, and that's this cone that kind of points, well, goes into this room if you want, and 0 is not included, of course. Now, if I want to condition it on BC, so I want, so my called-off gambles are actually the plane of the board, of the screen. So those are my called-off gambles. What is now my conditional model? Well, I just intersect my original set of desirable gambles with the plane of called-off gambles, and I obtain this conditional set of desirable gambles. So that's a very elegant way of conditioning. And also, of course, it's always well defined. There's no division through 0 or anything, so it's always well defined. And actually, it's always a coherent set of desirable gambles, and that's actually very easy to see. Because what is it? It's the intersection of a convex cone with a linear space of called-off gambles. And an intersection of a convex cone with a linear space is either empty or a convex cone itself. So the only thing I need to prove is that it's not empty. Why is it not empty? Well, this linear space of called-off gambles contains positive called-off gambles. For instance, 1 on E and 0 outside E. And every positive gamble is in my original coherent set of desirable gambles. So it's not empty, and therefore it's a convex cone. So the result is always a coherent set of desirable gambles. And it's exactly this border behavior, namely the guarantee that this part of my called-off gambles is always in it, that ensures that this conditioning is always coherent. So I think that's one big reason in favor for sets of desirable gambles instead of convex and closed set of probabilities. Another one is that marginalization, for instance, is very easy. And I will need this notation for later on, so I will explain marginalization now. consider a sequence of random variables, x1 until xn, and they assume values in this set, which is actually the product space of all the individual sets. And then for any subset of this index set, I want to find for any subset I of the index set, I want to find the I marginal. What is it? Well, I just look at my original set of desirable gambles on the sequence of gambles, and I intersect it with the gambles that depend on xi only. So I just take another intersection, I intersect it with the linear space of gambles that intersect on xi only, and my result is a set of is the marginal set of desirable gambles. So in fact, for any gamble on xi, this gamble is in my marginal if and only it was in my original one. So I think it's very easy and this is the reason that many proofs are very easy with sets of desirable gambles. So okay, I think we had enough about sets of desirable gambles. Let us now go back to our original problem of how to make choice under uncertainty. We have seen that sets of desirable gambles, they do the job for pairwise comparison, but in real life, many things are not determined by pairwise comparison alone. You need ternary or four-way or five-way or more comparisons. And that's when choice functions come into play. So what is the idea? Consider any set A of gambles. A is a non-empty but finite set of gambles, and we call it the menu or the option set. And then C of A is just the subset of it that I don't reject. It's a set of gambles that I choose in a way, or that are admissible to me. And what it actually is a non-rejected options. And R of A is a subset of A that is rejected. And of course, C of A and R of A, they form a partition of A. They partition A. And in order to do this more formally, I define the set Q. This is a domain actually of my choice function, and is a collection of all the non-empty but finite subset of gambles. So it's a subset of the power set of gambles. And then a choice function is just any map from this domain to the finite set of gambles with the property that any menu is mapped to a subset. So any such map is a choice function, and then its conjugate, if you want, is a rejection function. So rejection function is the same map, but with the same property. Now, as with sets of desirable gambles, is any choice function a good one? No. We'll focus again only on the coherent ones. Okay, those are the axioms. The first axiomatization for imprecise choice functions was actually done by Teddy Zeidenfeld, Schervers and Cadane. And I used a slightly changed version of it. I disregard two of their axioms. They impose an Archimedean axiom on it. I disregard it. And actually they impose also a mixture, something that has to do with convex mixture of gambles, and I don't want it. So what are my axioms I impose on it? The first one is that the choice of any non-empty set should be non-empty. That actually is a counterpart of avoiding Schur laws again. The second one is if gamble G is better than F. Again, this means that in any component of G is at least as big as the corresponding component of F, and there is a component in which G is strictly greater than the components of F. If this is the case, then F should be rejected from the binary comparison. 3 and 3b, those two are really at the heart of choice for me. The first one is what Amartya Sen calls condition alpha, and it basically says if I have two option sets, two menus, A1 and A2, and A1 is a subset of it. If now I reject an option from A1, it can never be promoted to an admissible one by considering the bigger menu. Imagine like this. Imagine you are at a restaurant, you see the menu, and you say, today I don't feel like eating burger. I don't want burger from this menu. And then the waiter comes and he says, sir, we also have a special menu today, which I didn't tell you before. Then condition alpha requires that now you should still reject burger, even when faced with a bigger menu. So I think it makes sense. Also, the 3b, it also makes sense, I think. 3b has to do with going to smaller menus. It says that if I have options that are rejected, if I now delete some of the rejected options from the menu, the remainder of the rejected options should still be rejected. You can think of it like this. I am at the restaurant, I see the menu, and I don't feel like eating burger and beef today from this menu. And then the waiter comes and he says, sorry sir, the beef is out, we are out of beef today. Then, item condition, it requires me to still reject burger. It's sort of, the rejected options, they sort of don't matter anymore to me. And then 4a and 4b, they have to do again with the linearity of the utility scale. So I can bring out any positive factor, real number, and I can add a common gamble to every decision problem, and the result should not matter. So those are coherent choice functions. Well, what can we do with it? Well, can we do binary choice with it? Well, at least we hope so. Because otherwise it's no generalization of desirability. If I have a set of desirable gambles D, now I want to find the smallest or least informative choice function that corresponds to it, or that is compatible with it. Now what do I mean with this compatibility? I mean that if a gamble F is desirable, is in my set D, then F should be uniquely chosen between 0 and F by my choice function, compatible with it. And what do I mean with the smallest choice function compatible with it? Well, if I have two choice functions, C1 and C2, I say that C1 is more informative than C2 if C1 chooses more selectively. If for any menu, C1 is a subset, so for any menu A, C1 is a subset, C1 of A is a subset of C2 of A. C1 chooses more selectively, I can, and if this is the case, then I'm more informed. And actually this relation, it induces a partial order on the set of all choice functions, and on the set of all coherent choice functions it's actually an ephemum lattice. So I can always take an ephemum with respect to this, and the result will be coherent. And actually, it makes sense to ask myself, what is the smallest choice function that is compatible with a given set of desirable gambles? And it turns out to be this one. It identifies the undominated gambles in A. So what is it? It are the gambles F and A, such that there's no G in A that is better than F, according to my set of desirable gambles. So this is what I call my binary choice function, or at least the least informative one. And it's actually more easy to see it in terms of rejections. 0 is rejected from an option set if and only if there's at least a desirable gamble in it. So this intersection is not empty. Is there a smallest choice function? Yes. It turns out that there's a unique smallest choice function, and it's the one that rejects that rejects 0 if and only if there's a positive gamble, again with this relation pointwise non-strict, but as a gamble not equal, in A. So if there's such a gamble in A, gamble that I will surely win something, well, or at least don't lose anything, and there's at least a chance that I win something, then I reject A. Then I reject 0 from it. Otherwise not. So that's the smallest, uniquely smallest choice function. It corresponds to not knowing anything at all. And coincidentally, it's also the choice function that corresponds, it's a purely binary choice function. So it's a choice function that corresponds with the vacuous set of desirable gambles. So we have seen how we go from a set of desirable gambles to a choice function. can we go the other way around? So this is a one-to-many, and this is the unique smallest one. Can we go the other way around? Yes. If I have a choice function, then I just look at its binary behavior. I can always plug in any finite sets. So in particular, I can plug in binary sets with 2 elements. And the gambles f that I choose uniquely from C, those are my set of desirable gambles. This is a many-to-one relation. So many different choice functions map to the same set of desirable gambles. And what is important? Well, important is that in both directions coherence is preserved. And actually, for both proofs, I need all the rationality requirements. So I don't have too many rationality requirements, if you want, to make a link between choice functions and desirability. So now what can we do with choice functions? Choice functions, they include many or most of the popular decision rules extant in literature. For instance, it includes Wallis-Sen maximality. That's actually an instance of the CD before. And also it includes E-admissibility. And E-admissibility, that's, imagine you have a set of probabilities. Then the E-admissible options are those options that for at least one probability in it has the highest expectation.
Sorry, can you slow down a bit?
Oh, sorry, of course.
So let me try to clarify. So on the previous page, you said that so C of D, that is to say that if I have a set of desirable gambles and let me design a choice function, there could be many, but let me give you the smallest one.
Yeah, this is the smallest one that's compatible with it. Yes.
But you said that maximality is what gave rise to this.
Yes, this is actually Wallis-Sen maximality. It identifies the undominated options under this partial order.
I see. So this would be a choice function derived from the set of desirable gambles.
Yeah, one of many.
If you want to be maximality, if you want to respect maximality.
Well, no, this is the smallest one, and quite interestingly, it is the one that corresponds to maximality. So maximality is like the most conservative decision rule, based on a binary preference, if you want.
And it is the smallest one in the sense that if, can you say that again, what it means to mean that this is the smallest?
Yeah, the smallest one, imagine you have 2 choice functions, C1 and C2.
Yeah.
C2 is more informative than C1 if for every menu, C2 of A is a subset of C1 of A.
Okay. So
if I choose more selectively, then I'm more informed.
But so the set of desirable gambles, the way that I think, did you say that if you have a set of desirable gambles, it means that I know how to make all pairwise comparisons?
Yes, exactly.
I see. And
but not necessarily ternary comparisons or four-way comparisons.
I see. So this C of D would always give exactly what the D would do for pairwise comparisons.
Yes.
And for the 3 and 4 and so on, that would be the smallest.
Yeah, it extends to higher comparisons in the smallest way, smallest coherent way.
And then if you were to use E-admissibility instead, you would get something other than that C of D.
Yeah, that's a strictly bigger one.
Okay.
But it's a popular decision rule in the literature. But it's not the least. So here you assume other things than coherence alone. If you base yourself on a partial preference relation, on a pairwise comparison between gambles. Now I want to do the same things as before. I'm conditioning and marginalization, and then I want to finish with a notion of symmetry and exchangeability. So conditioning for choice functions is also very elegant, and it's the same idea. I start with the choice function C, and I have a conditioning event E. What is my conditional choice function C given E? Well, for any menu A, it identifies those gambles in A. A is a set of gambles on E. It identifies those gambles in A for which the called-off version is chosen by the original choice function. So I plug into my original choice function only called-off gambles, and I look what it returns. And actually, so now I have a definition of conditioning choice functions, conditioning set of desirable gambles, and going from a choice function to a set of desirable gamble. Actually, those operations commute. So if I have a choice function, I first go to its binary, pairwise behavior, and then I condition. That's the same thing as conditioning my choice function first and then going to the pairwise behavior. So that's kind of what we want. Also, marginalizing is very easy. I have, again, a sequence of random variables that take values in the product set. Then for any subset I of the index set, the xi marginal choice function is the one given by the original one if I only plug in gambles that depend on xi alone. So that's, in my opinion, this is really elegant. So now, okay, I try to convince you about the elegance of choice functions and desirability, but now, and choice functions and desirability, they are actually a near reflexive statement. If I find a gamble desirable, that's a strict assessment, and same for if I reject a gamble, that's a strict assessment. That's not, I find it equal to another, to a chosen one, no. It's strictly worse than a chosen one. Now I want to reconcile it with some equivalence relation. I want to reconcile it with indifference. So imagine that, we start with a set. So indifference is a structural assessment which I want to reconcile with choice functions. Imagine that we have a set I, and set I is the set of gambles that I think are equivalent in sense to 0 to me. So you can think of, so if I contains a gamble f, then f and 0, I want to swap them. It doesn't matter which one I have. I want to if I compare something with 0, it should give the same result if I compare it to f. Okay, and I will assume that I is a linear space that has nothing in common with the positive nor the negative portent. Why is that? Well, if something is positive, then it is already desirable, and hence strictly preferred to 0, and hence not equivalent to 0. So I want any linear space that has nothing in common with the positive nor the negative portent is a set of indifference options for me. And okay, if I have a gamble G in my linear space in I, then G and 0 are equivalent, and therefore also F and F plus G is F and F plus G are equivalent. So this induces an equivalence class on my gambles. If I have a gamble F, then if I add any indifferent gamble to it, the result will be equivalent to F. And I will denote this equivalence class by square brackets of F. And actually the set of all those things, of all those equivalence classes, is a quotient space. And the quotient space is a real linear vector, is a real linear space. And actually it's an ordered real linear space. Before I have defined choice functions and sets of desirable gambles on the real linear space of gambles, which is also an ordered space. This was not necessary. I could define it on any ordered real linear space. For instance, on the quotient space. So now what is my definition of indifference? Or when is the choice function compatible with this assessment? Well, it is compatible with this assessment if there is a representing choice function on the quotient space. And what do I mean by this? I mean, by representing, I mean that it completely returns or uniquely defines my original choice function. So C is compatible with I or reflects my indifference statements if there is a representing choice function C prime such that on this lower dimensional space, such that my admissible options are the options in A that are admissible or whose equivalence class are admissible by this simpler choice function on the lower space. And you can think of it, my original choice function, it chooses between dots, between gambles. My representing choice function, it chooses between equivalence classes, so lines in this picture. And that's way easier, because here we had 6 gambles to choose between. In the representing choice function, we only have 3 lines to choose between, which is a way easier choice problem. So by adding an indifference assessment, we typically reduce the complexity by the choice problem.
Can I think of this as if you are constructing equivalent classes of choice functions also?
Equivalence classes on choice functions. So 2 choice functions would be equivalent with each other. I don't see that.
Maybe that's not the right word for that.
I like to think about it. I start with an extra assessment, I. It's a linear space of gambles that are equivalent to 0 of me. And this simplifies, or this induces a quotient space of gambles which is simpler. So instead of dots, in this picture I have lines.
Right.
And my representing choice function, it chooses between the lines instead of the gambles. And there are typically way less lines than
So
dots.
that's kind of like reducing it's kind of like marginalizing, right? Because you're marginalizing over this way. You used to have a 2-dimensional thing. Now you're just looking at every line being indexed, and then you can compare. Actually, you're marginalizing this way, so orthogonal to the lines.
Yes, in a sense, yes. In a sense, you can think of it this way, I guess. Yeah. Yeah. Okay, so this is our definition of indifference. And it's actually very, very similar to the existing definition of indifference for desirability, which is given here. A set of reliable gambles is compatible with I, or represents an indifference statement, if this set of reliable gambles D is completely determined by its representing set of reliable gambles, not desirable gambles, but set of desirable equivalence classes. So I think it's very elegant and quite clear what this means. So there are some properties. First of all, the representing choice function is unique and is given by this formula. So if I have an original choice function that is indifferent, or that is compatible with I, then its representing choice function is uniquely given by this formula. Second, and this is quite important, my original choice function is coherent even only if the representing choice function is coherent. And this is important because now I can do all the probabilistic inference in the lower dimensional space. And then after I've done this, I just check whether the result is coherent, and I go back to my original one. And it's typically way easier to work in this space. It's lower dimensional.
What does that symbol mean, CA slash?
This, it means the set, okay, this is a set, and by /I mean the set of all equivalence classes from this. So I take any element of this set, and I take its equivalence class of it.
I see.
Yeah.
I see.
Okay, so now I turn to the last part of my presentation, exchangeability. And exchangeability, well, of course, we have a sequence of random variables, and it's studied by Definetti, of course. It's a weaker assumption than independence, so that you can learn from past trials, so past observations. Loosely speaking, what it means is that it says that the order in which I observe the random variables doesn't matter. Or more formally, if I have an observation, I have a permutation of the index set. This permutation, any such permutation pi, it yields a new observation in which I just change the order. I can lift such a permutation to the set of all gambles on the observations, on the sequence of random variables, and this lifting is just applying it one after the other. So the lifted version of f, the permuted version of f, is just f evaluated in the permuted order. So this lifts P or pi to the set of all gambles. So now I can permute a gamble. And now what does it mean to be exchangeable? Well, formally it means that any gamble F and any of its permuted versions are considered to be indifferent. So they are equivalent or indistinguishable from each other in a sense. And therefore I needed well, for this I needed the indifference from the last slide. Or in other words, a choice function is exchangeable if and only if it is compatible with this specific linear space of indifferent gambles. So what is it? Well, I take the span, the linear hull of any gamble minus its permuted version, and this for any gamble and any permutation. So now I already have a representation theorem if you want. A choice function is exchangeable if and only if there is some representing choice function C prime on the set, on this set, on this quotient space. Now, of course, in a way, this is a generalization of de Finetti's famous representation result for exchangeable probabilities, but it's not a very nice one. In particular, this set is a very ugly one. What does it mean? This equivalence, well, this quotient space, it has no clear meaning. So let us go back to the definition of exchangeability, and let us, in order to find a real generalization of de Finetti's results, well, what does it mean to observe something and to permute it? Say that I observe A, B, A, B, A, for instance. If I permute it, for instance, the result will be B, A, A, B, or A, B, 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 or sorry, A, B, B, A, and so on. What remains unchanged, or what remains constant in this, when I do this? Well, the counts remain constant. The number of times I observe A, and the number of times I observe B in the sequence, they remain constant. So let's focus on this. Let's focus on the count vector. The count vector, g of x, well, it's for any x, this is a vector. So for any observation x, this is a vector. And its z component for any z in the outcome is just the number of times that z occurs in the sequence x. So for instance, in this sequence, then A would be 4 and B, its B component would be 2. So the count vector of this sequence is 4, 2. Right? So now, what is the result of a count vector? What is a count vector, or what is the result of the map T applied to an observation? It is a set of all count vectors. It's a set of all vectors with integers as components that are non-negative and that sum to the length of the sequence, sum to n. Now, when I have a count vector m, it's a vector, what is then the invariant atom, or what is then the set of all sequences with this particular count vector? Well, it's of course it's this. And let me look at how many elements are there in it. Well, there are n choose m elements in it, or this number. And now, quite interestingly, if I apply the uniform over this set, so I have any m, I fix a count vector m, and I apply the uniform expectation to it. It's this thing. I sum. For every gamble, I sum in all the possible y's, in all the possible invariant atoms, and the mass is of course 1 divided by the number of elements. This actually, this characterizes a hypergeometric distribution. So actually, it characterizes sampling from an urn with n balls, and the composition is m of this urn. And this is quite interesting. Why is it interesting? Well, because this map, this thing that defines a hypergeometric distribution, it is a linear order isomorphism between this ugly set in which I had an original representing choice function and a set of all gammas on count vectors. And if there's a linear order isomorphism, then actually I can express my choice function in this or in this set. It doesn't matter. They are equivalent for the choice function. So now I have found a more general generalization of the phonetics result. A choice function is exchangeable if and only if there's a representing choice function on the gambles on the composition of the urn. Or in other words, my exchangeable choice function is completely characterized by choosing between gambles on different compositions of urns. So I have a belief model on compositions of urns. And I think this is a particular nice generalization of the phonetics result. I would like to end my presentation here. I will quickly review what we have seen. So I hope to have convinced you that sets of reliable gambles and choice functions are quite elegant and easy to work with. And also I haven't talked about it, but since it's it models the behavior of a subject quite directly. It looks directly at its choices and its decisions to be made. So I think you can apply it. I think it's easily applicable to real life situations. And at least I know one decision problem you will all be faced to next summer. That is, to which conference shall I go to next summer? And let me help you. I think that the ISIPTA conference is a nice one to go to. This was my presentation. Are there any questions, or I don't know how it goes now?
So the choice function idea, which is generalizing the desirable gambles idea.
Yes.
Did I get it correctly that the choice function, there's this indifference element. It doesn't pick out one element necessarily.
No, yeah, if it picks out one, then you have a very maximal one.
But it might pick out several.
Yeah.
So, is there any idea of this being operational? Because
yeah.
you give somebody a choice, they pick out one, right? You don't see what they did.
No, yeah. There's there's an idea to make it operational. Actually, there's very promising work, I think, now by Gert and Jasper de Bock. And it uses almost the same. Well, let me first tell about the defect of this axiomatization. This is the one I used in my dissertation, and I think it contains a defect. It's too weak because there are choice functions, there are coherent choice functions that cannot be written in this form. That are not unions over a set of reliable gambles of this form. Actually, with a very small modification to 4a, this would be the case. That every coherent choice function can be written as this form. I should explain it better.
You have to remind me what the symbols mean.
Yeah, I have a curly D is a set of sets of desirable gambles. So it's a collection of pairwise belief models that correspond to pairwise comparison. And wait, I will here have a bit more room. For desirability, we have let me think how to.
Should I understand this curly D as a collection of agents, say?
Yeah, you can think of it like this. Yes, yes, yeah.
Or is this trying to reconcile between, say, yours and my belief?
Yes, in a way it is. Yeah, so you can think of this D. Okay. What I actually wanted is that every coherent choice function actually is equivalent to a set of desirable gambles. In much the same way that every set of desirable gambles, well, it's not equivalent to a set of probability mass functions, it's actually equivalent to a set of lexicographic probability mass functions. And in the same way, I wanted that every choice function is equivalent to a set of sets of desirable gambles, or a set of partial orders if you want. And through this relation, if I have such a set of partial orders, then for any menu, the choice by any, so this is typical, this defines a coherent choice function. And any coherent choice function should have a unique set of desirable gambles. Well, if this is not the case with this axiomatization. This is not true. With a slight modification to 4a, this is the case. And then we can interpret, if this would be the case, then we can interpret the choice function through set of desirable gambles. And then it would mean simply this. An option U is not chosen from a menu A if and only if, or sorry, an option F. And if and only if there's a gamble G in A, and there's a set of desirable gambles and it's representing set of desirable gambles such that G minus F is in D. So an option is not chosen if there's in the option set at least one better to at least one model. And this gives.
It's chosen if there's at least one better. It's not chosen.
It's not chosen if there's one better. Yeah, if there's one better, then you don't choose this, right?
Hold on.
And this somehow makes, if this were true, it would make it more operational.
Well, if sets of desirable gambles are operational, then choice functions would inherit this meaning. Because you can express everything in terms of sets of desirable gambles.
Oh, so you would have to find out somebody's, you have to present them with many different menus.
Yeah, for any menu. So for any menu, for all menus, there's the D, so that for all menus this holds.
And the example where it doesn't hold, you don't like?
The example is, well, the problem with 4a is too weak. I will. For A basically says this: if I have a menu of this form and gambles, then 0 is chosen from it if and only if 0 is chosen from any such choice function where I multiply it by a common lambda for every gamble. And lambda is positive. And this is too weak. What I really want is this. Or what I needed, but I only knew it afterwards. Was that I could choose the lambdas independently from each other. All positive, but independent from each other. And the counterexample that I have in my dissertation, actually it's a there's a coherent choice function. If I have here f, and here I have 2f, then I have a coherent choice function that says that 0 is chosen from 0 and f, but 0 is rejected from 0, f, and 2f. Which doesn't make much sense, I think. Well, and this, by choosing the lambda for this gamble 1/2, it maps to this option set. So it's made illegal by adding this axiom. So that was a defect in my dissertation, I think. I don't know, was that your question or did I misinterpret it?
Yes, I think it answers my question.
Okay, okay.
Partly, yeah. It answers more than my question.
Okay.
So I'm wondering, so I'm now going back to just the gambles and coherence condition.
Sure.
So this is, I guess this is a fine set of conditions, but I guess what got me was when you described the upper provision as the minimum price you would sell, right?
Yeah.
The gamble, and the, right?
Yeah, exactly.
And the lower provision is the maximum price you would pay for it, right?
Yeah.
So what's the problem? Oh, but the gambles are represented as just, so I guess what I don't see is why this relationship on the next page or whatever it is, in terms of the upper and lower being expressed in terms of one another. You know, like Glenn was saying, I guess, operationally, it's different for me to accept a bet you offer me because I'm only going to accept things if I think you're offering me something good, and it's different than for me to offer you a bet which you can just choose to decline, right? Because, so I'm thinking of a situation in which if I might offer a bet, a gamble, so I think a gamble on a coin flip, which pays $1 if heads,
Yes.
and loses $1.10 if tails, right?
Yes.
So I would be willing to offer that bet for free, for nothing, right? But I might be willing to accept a bet which would only pay $1.05 and lose me $1, but I wouldn't offer it.
You wouldn't offer the negative of it.
Coherent. That would, what's that?
You wouldn't offer the negative of it.
I would not offer the negative. I would not. Yeah, I guess however you have to add the negatives in. You know, I'm offering.
Yeah.
So I wouldn't. So that would be incoherent according to this. According to this somehow, because this condition wouldn't be satisfied.
Can I write it down now? What you're saying?
There's a
So you have a gamble.
distinguishing between positive and negative numbers here.
Well, yes,
whereas,
but the reason that they're different is because of, and I think it's part related to your point, which is that there's a difference between offering a bet and accepting a bet.
as long as
I agree so,
as
but
the bets are always positive payoffs.
yeah, that's a point. If I specify my supremum or my supremum desirable buying price for any gamble in a linear space that also contains a negative of it, then I immediately specified the selling price, because here if I specify this for f and for minus f it's actually specifying the upper provision.
So you don't have to.
But minus f is also a gamble, which I can buy, but buying minus f is actually selling f. That's the same thing.
One way, a verbal way of saying it is that selling something for A is the same as buying it for minus A.
Yes, exactly.
So that means you're thinking, you've already, in his mathematics, you're already in this place where what you're buying or selling could be positive or negative. You might not like that. We might want to theory. I think Harry is proposing, we think in terms of
Horse lotteries.
someplace where we only sell things and buy things that have positive or non-negative.
Like the theory of horse lotteries we do, like horse lotteries, for instance, we do. Horse lotteries, or
Horse lotteries.
horse lotteries, yeah.
Yeah, I mean everything is phrased in terms of positive payoffs.
Yeah, you can do it, yeah.
So if you only phrase everything in terms of positive payoffs, you've got to make your set of conditions more lengthy here. And some of them, Harrier, I might not like, I suppose.
Well, I'm actually thinking about, a sports book, which would not offer you one-to-one on both sides of the bet, but they would offer you, minus 110, whatever it would be. It would pay you 10 to 11 on both sides.
Yeah. But not 11 to 10, right? No, yeah. And that would be the
And so that would be saying, okay, I'm taking the cut, right? But if I'm running a book, I'm going to charge this percentage, right? But if I go and I see if I see a bet on if someone else is offering a bet and I think I have a positive advantage, like this 105 minus 1, I might bet that, but I'm not going to offer that bet.
Yeah, so you're saying that
Because
the lower provision of it is 0, and your upper provision is what? It's bigger than 0, right? Yeah. So you want to offer it, but you don't want to sell it. Oh, sorry, you want.
That's right.
Yeah. So, but that's coherent. I don't see why. Yes. Yeah. It's imprecise because
It's not asking you to be able to sell and buy it at the same.
No.
It's you'll be willing to sell the negative of what you're willing to.
Oh,
so
okay.
there's a double.
I guess I am confused then by the negative. Okay, I see.
Yeah, I think this is coherent for sure. So actually, it gives you.
Oh, okay.
For any given, you can think of it like this. For any given gamble, I have a line. In the precise case, I have a fair price. That's a definite expectation. It was a fair price. It means that for everything less than that, you want to buy the gamble. And for everything above it, you want to sell the gamble.
Yeah,
That's, and now, instead of a fair price, we have just a lower and upper bound. And the lower bound means that for anything less than that, I want to sell it. For everything more than it, I want to, for anything less than it, I want to buy it. For anything more than it, than this bound, I want to sell it. And between there's some indeterminacy. I don't want to do anything, or I state that I don't want to do anything. Or I don't state that I want to do anything here.
Right. Okay. Yeah. That's fine.
Are there more questions, or?
Maybe we could continue over there. Okay.
Great.
All right, thanks.
Thank you.